Welcome to this lesson of Introduction to Blockchain presented by Coding Bootcamps. This is blockchain consensus. We've covered information about your instructor and what we have learned so far. Well, in the previous lesson, we covered cryptography. Before that, we talked about hashes, types of blockchains, private, public. We've talked about blocks and how they're constructed. So now we're going to take a deep dive into blockchain consensus. So consensus and the truth of the blockchain. You'll often hear the consensus referred to as the truth, interestingly enough. And so consensus is necessary because there are multiple nodes. The idea that these nodes all contain the same ledger. So the ledger, it's supposed to be one ledger, many nodes. So the ledger is actually running on different computers, which means the ledger configuration, the data, however you want to discuss it or indicate it, can drift a little bit. So there may be times where the ledgers do not agree, and they have to agree. So blockchains have consensus algorithms that bring all the ledgers on all the nodes into synchronization so that all the copies of the ledger are identical again. So quite often this is referred to, like I said, as the truth. So we have proof of work, and that is, I agree, is a very mature, or the most mature consensus algorithm. I do agree with that. And so whoever wins a proof of work, whoever is able to solve that puzzle, is able to then broadcast his or her validated transactions of a single block. So let's remember that blockchains are built one block at a time. So if I win the proof of work, I'm only sending the most recent transactions to the other nodes. So it's just one block, and that is our new version of the truth. And proof of work, again, is what Bitcoin uses. However, other consensus algorithms are beginning to quickly emerge. So with proof of work, it's an economic measure it was started off as a way to deter denial of service attacks and service abuses such as spam, by requiring work to be done of a service requester, usually meaning processing time by a computer. The idea was you have to really want to send out whatever you need to send out in order that you would complete this work. A key feature of this schemes is their asymmetry. Right? The work must be moderately hard on the requester side, but easy to check for the service provider. And so the idea, also known as the CPU cost function, client puzzle, computational puzzle, or CPU pricing functions. Either way, the proof of work consumes a lot of energy, and it's very expensive and quite time consuming. So with proof of work, you can almost think of it as a CAPTCHA for a computer. If you're familiar with CAPTCHAs, a CAPTCHA is intended for a human to solve quickly. Rather than a computer. When a block is full, each node competes to solve that guessing game, which is the proof of work. So we talked about that earlier. So they're competing to find the nonce. So they're running random combinations in order to find that nonce, in order to create that hash for the block that everyone has just been validating. So the miners have all been validating the transactions, and now they want to hash that block. So a miner will answer the relays. So once a miner actually has that block, he or she relays that new block to the rest of the network, and all the miners confirm the solution by trying their nonce on their own blocks. And if 51% of the miners agree, the block is added. Well, that happens to be how it is with blockchain. It does not have other blockchains can certainly have other rules, but 51% happens to be Bitcoins, what the Bitcoin community is currently using. There's also proof of stake consensus. So that's another consensus algorithm. It's definitely an alternative to proof of work. Um, with proof of stake, you don't run random numbers until the number is found. So it's considered much more green, consumes a lot less electricity, a lot less energy. And the proof of stake, the miners all bet a small amount of their existing cryptocurrency for that blockchain. And the miners that bet and honestly follow the rules can win back their bet. When I say honestly follow the rules, meaning they are valid in validating the transactions. So they're honest in validating the transactions. The miners can keep betting, and if they follow the rules, they will win back their bets. Any kind of rule breakers will lose their bets. So the action here, a block is filled, and at the time of the group consensus, all who wish to participate in the group consensus essentially stake or bet their funds. And a player is selected at random. So out of maybe 25 of us, one person gets to reveal his or her block with the validated transactions. The player's block is revealed to the other players, and if the majority of players differ with the block data, the player loses, and loses the amount of cryptocurrency he or she put up. So the stake is lost. So it certainly pays to be honest. Ethereum is moving to proof of stake, and proof of stake is promising as, again, it is a reliable consensus algorithm and is much less expensive. So with proof of work versus proof of stake, again, there is no processing during consensus. There is a criticism that proof of stake, well, could be centralization. Proof of work is not at all centralization. I guess that argument will continue to go on, and then we will see where it takes us. Proof of stake is still new, whereas proof of work is very mature. And then some other blockchain consensus algorithms. There's the proof of activity. It's a combination of proof of work and proof of stake, where blocks are mined and confirmed with proof of stake. There's also proof of burn. So proof of burn involves sending coins to what's called a dead address. So a dead public key, and then blocks are mined and confirmed with proof of stake, and then the coins burned. The more coins burned, the better chances of being selected to be the next one to mine the next block and win the reward. Proof of space, which is getting some attention. Proof of space proposes we apply the same principles as proof of stake by allocating a dedicated amount of memory or disk instead of CPU time. And if you allocate more space, the better your chances are of mining the next block. And proof of elapsed time, similar to proof of work, but it runs on a custom, more efficient environment. So consensus is very important for the operation of the blockchain, particularly where there's only one ledger and all nodes are equal. Consensus is obviously important no matter what. There are blockchains where all nodes are not the same, where there are different nodes. Hyperledger Fabric and also Corda, there are specialty nodes there, but we don't have that with Bitcoin. So it is critical on a Bitcoin or Ethereum network. Ethereum, all node, there's just one node type on Ethereum too. It's critical that the ledgers always agree, so the community needs some kind of a consensus. So we discussed again, in summary, our proof of work consensus. Proof of work is solving a very difficult mathematical puzzle. The important things to take away from here are definitely proof of work and proof of stake. The other algorithms are important, but proof of work is obviously what's used, is very popular right now, and it is in use. And proof of stake, it seems to be the consensus algorithms that a lot of blockchains are moving toward. And again, let's look at our assessment. And also for additional resources, consult your learning materials. And if you're interested in more training, also consult your learning materials. And in our next session, we'll talk about distributed networks. So thank you.